So we're going to be moving now to the proton NMR. We want to have a look at the spectra, and then we've got another widget coming up in a minute about that. Okay, so I think one of the key things to note, so should we first of all have a look and work out how many different proton environments there are within ethyl benzene?
Okay,
it's slightly different to the carbon environments.
All right. So we've got spectrum to begin with. So we've got essentially, as you've seen, the CH2, the CH3. So first things first is we've already seen there are 6 resonances in the carbon spectrum, and well, there may be less in the proton. The reason there's less really is that this carbon here is not attached to any hydrogens. Okay, so that carbon it's already got 4 bonds, so it won't have a hydrogen. So you'd expect to see, let me change colour because otherwise it's been very confusing. We'd expect to see one here, another one here, okay, and then actually because these are all very similar, we'd expect to see kind of one signal because it's fairly, because the separation is much less in proton NMR, one signal due to all of those hydrogens.
Well, certainly, as it's similar to the case that we had with the carbon, it's quite hard to assign those. So what we would like you to do in the next widget, so I shall get that up now. So one of the differences between carbon and proton NMR is that with proton NMR, because it's much more abundant, we can actually use the integral, so that would be the area under the peaks, to actually assign the number of protons in that are contributing to that resonance peak. So what we would like you to do here is to work out what the ratio you would expect to see for the integral is for the aromatics compared to the methylene compared to the methyl protons. So if you have a go doing that, and to say while you're looking at that, then Nick is going to talk us through a little bit more about this particular spectrum.
Okay, so this is a proton NMR, and I guess the first thing to say, as it's the first time we've seen one tonight, is it doesn't run from 0 to 200, it runs from 0 to about 10 or 12 or whatever, so much lower values. Again, it's chemical shift along the horizontal axis, and again, it's measured in parts per million. Okay, but what we're going to really just do is just identify some of the peaks, isn't it? Okay, yep. So just as we did with the correlation chart for the carbon, we're just going to use the correlation chart to identify some of the peaks in ethyl benzene. So we've got some peaks around 7. So what might they be, Eleanor?
Okay, so in this case, we're looking at the correlation chart. So the correlation chart we're looking at here is the one for protons attached to multiple bonds, because we are looking at the aromatic ring first of all. And you can see here for the aryl ring protons, we would be expecting those to resonate between about 6.5 and 8.5 ppm. So I think that is consistent with what we're seeing.
About 7.3 or something like that.
Okay, so we can attribute these to the aromatics, and you can see here quite clearly that you can't really resolve it very well. There's a whole bunch of peaks, particularly at this magnification, so it's quite hard to attribute anything more precisely. Okay, right, so I'm going to swap correlation charts now. So with proton, we have a lot more correlation charts. So I think the next one we're going to look at is for the methylene. So for these ones here, so the methylene, so we need to look at the methylene correlation chart here, and we are looking for the protons on a carbon attached to an aryl group. Is that right?
Yep.
So we would be looking at down here. So this is the AR, stands for the aryl, so kind of aromatic, and it is, I think, this one here, so roughly 2.5 to 3.5-ish ppm.
Yep, and ours is about 2.7 in our spectrum, so that fits quite nicely.
Okay, and then the last one is the methyl, so we now need to look at the third correlation chart for the proton NMR, and we were looking at, it's the carbon really attached to the attached to the methylene and the aromatic. So I probably would be looking at this one around here. So where's that? Roughly around 1 to 2?
Yep, 1 to 2, and ours is about 1.3 ppm, so that fits all quite nicely.
So is it worth pointing out that this is an impurity?
Yes, this is probably an impurity due to the solvent. So this is not you probably can't see, but you might be able to see. We haven't integrated this line, and the reason we haven't integrated this line is we know this comes from an impurity, so there's nothing to worry about there.
Okay, right. So I think it's back to the widget now, and yes, the vast majority of you here have got a ratio of 5 to 2 to 3 for the aromatic to methylene to methyl
which is
so
exactly
I think
what we expect, isn't it?
it is what you expect. So we've got one here now.
I've got
with
one
the
which is just
integral.
very quickly, just to reiterate what you've already seen really. This is a 5 hydrogens because you've got the 5 aromatic protons there. You've got the 2 hydrogens for the CH2 group adjacent to it, and then the 3 hydrogens for the CH3 at the end. Okay.
Okay, right. So what we're going to do now is we're going to look at a different molecule.
Yes.
So we are going to look at pentyl propionate.
Right.
So Nick is going to draw this out so you know what it is, but this will relate to the next widget as well.
Okay, so the reason we chose this molecule is that I know that in the slide cast you look at ethyl ethanoate, which is an ester, and esters have some quite commonly looked at as good introductory examples because of various features associated with them. So we're going to look at another ester, and the ester we're going to look at is pentyl propanoate. So let me just draw that out for you. So it's an ester, so I'm going to put the ester function in first of all. And it's propanoate, so we have 3 carbons in the bit containing the carbonyl. So that's the propanoate part. And then I'm just going to put the hydrogens on so we can see those. And it's pentyl, so the branch off propanoate has 5 carbons. Let me just put those 5 carbons in, and then let's fill the hydrogens in accordingly. So making sure that everything has the right number of bonds, essentially. So that will be the structure of pentyl propanoate.
Okay, right. So this is where we're now going to refer you to the next widget. So widget number 3, we would like you to identify the number of proton resonances that you would expect to see for pentyl propanoate. Okay, so if you have a go answering that question, so again, you're very much thinking about the different environments that you will have there for the protons within that molecule. And while you're thinking about that, we are going to look at the carbon-13 NMR spectrum of pentyl propanoate.
Yep. Let me just get that. So we've got, again, a labelled structure here of the pentyl propanoate or propanoate, depends on which source you used in terms of that naming. But particularly we're going to look at, I guess, 2 main peaks here, okay? We've got we've got a lot of peaks kind of low down value, which we're not necessarily going to focus on just yet, okay, because essentially they're going to be quite hard to identify. And the reason for that is they'll be to do with these CH3s and maybe those CH3s, a long way from the oxygen atoms, which are pushing the chemical shift upwards. So we're going to focus on the peaks around 175, so this peak up here, and also this peak around 65. I should also point out that these multiple peaks is actually again due to the presence of our CDCl3. So we're going to focus on those 2 peaks and look at essentially what they're due to. Okay, so let's get a correlation chart again for that.
Okay, so as Nick said, these ones really are to the, as we saw in the previous example with the aliphatic carbon. So these are the ones that stay in the chains. So we're focusing on the other 2. So what we're looking at here then is for the carbon in a carbonyl. So there are a number of examples given on the NMR correlation chart. We don't actually have a carbonyl on here for an ester, but you would expect it to be very similar to that for an acid. And that's around 160 to just over 180 parts per million. So that fits quite nicely with the one that we're seeing here at 175.
Yep.
The other carbon that we're talking about was the carbon that was joined to the oxygen of the ester. And in this particular case, it's around about 60, around about 60, centred around about 60, so somewhere between about 45 and 75 ppm, yep. And I think that agrees with what we've seen here.
Absolutely, this is about 175 for the carbonyl of the ester group, and then the oxygen, the CH2 adjacent to the C adjacent to the oxygen is around 65.
Okay, so this is another example here where you can see the electrons with the electronic environments, in this case because this carbon, for example, is attached to that electronegative oxygen, that we are seeing kind of greater de-shielding due to the fact that it's next to the electronegative oxygen, which is why we're going to a higher shift,
yep.
Higher chemical shift. Okay, the other effect that we would see for the electrons is the electrons in the intervening bonds actually enable coupling between NMR active nuclei. So that's one of the things that we're going to be looking at now, is kind of the idea of the spin-spin coupling. So say again, there's a lot more on the theory of that in the NMR, the fundamentals, so we're not going to really talk about that now, but really how you recognise coupling patterns and when they're likely to arise. Okay, so I think that's the next thing. Isn't it?
Yes, that's the next thing. So we're going to look at a coupling actually in a carbon NMR. And what we currently have here, this current spectrum, which we've got recorded by Matt, okay, that what you have here is actually you don't have any coupling. It's a so-called decoupled spectrum. And what we're going to try and do is predict what coupling we would see in a so-called off-resonance carbon NMR, okay? So we're going to, again, just going to focus on the two peaks we discussed before. So let me just write out the kind of fragments associated with this one around 60 odd was the oxygen with the two hydrogens, and then I'm just going to do a squiggle for the rest of the molecule. So that's this one here, okay? So this is this carbon that's directly bonded to two hydrogens, and hydrogen is an NMR active nuclei, so can therefore interact with the resonance of carbon and essentially split the signal, okay? And the rule that you may well have seen before is this N+1 rule, where N is the number of active nuclei, of NMR active nuclei that are interacting with a nuclei of interest, I suppose. Right, so so we're looking at the interaction between this carbon and those two hydrogens. N is therefore 2 because there are two hydrogens that interact with it. So this line would in fact be split into 2 + 1 ways. So it would be split into split 3 ways to give me an overall a triplet. So we'd mark that normally, predict it to be a triplet normally, okay, in the off-resonance spectrum, okay. So let's look at the other one, which is the ester, the carbonyl carbon, okay. So this isn't bonded. You can see maybe on the picture above it a bit more clearly. This is bonded to no hydrogen. So in this case, N is 0, okay. So therefore, rather than seeing any splitting, we just see a single line. So this would end up just being a singlet, as it is in the decoupled spectrum.
Okay, and I think the key thing to note here is with the off-resonance that we're just we were just looking at the nuclei adjacent to the carbon, so just the ones that are bound. So it's just going to be the hydrogens that are bound to that or that carbon nucleus.
Yep.
Okay, right. So I think we're going to be looking at the proton NMR in a minute, but I think the first thing we need to do now is go back to the widget and identify how many different hydrogen or proton environments we would expect to see. So in this case, I'll just plump for one. Okay, so we've got a bit more of a mixture of results here.
Okay.
So we have 53% are going for 7, 33% for 6, and 13% for 5.
All right, so we'll go out to the big picture we drew before to work out what the right answer is. So essentially, we're looking at the hydrogens here. So let's just start with the CH3 at the end. The first thing I suppose to point out at this stage is to make sure you're all aware that all those 3 hydrogens, or the ones that attach to the same carbon, will all be in the same chemical environment. And the reason for this is we essentially get free rotation about the carbon-carbon bonds, which means essentially these hydrogens are changing place very, very rapidly. So we get one chemical environment for that, one chemical environment for that, etc. So therefore, this is one chemical environment. The CH3 is one chemical environment. The CH2, adjacent to that, is a second chemical environment. So that's the first two. Let's just move along to the pentyl branch. Well, okay, so this is a CH2, but it's a different CH2 because it's next to an oxygen rather than next to a carbonyl. So that's a third chemical environment. Then as we go along the chain, hopefully we can kind of see that they're all going to be different because they're all going to be kind of further away from the oxygen, aren't they? So this one is 2 away, that one is 3 away, etc. So this will be a fourth chemical environment. This one here, these hydrogens here, will be a fifth chemical environment. Those two will be a sixth. And those last 3 will be a 7. So the right answer was actually 7 chemical environments.
Okay. And there is actually a question related to the aromatics. So we will come back to that one in a minute about the aromatic protons, but we'll come back to that. We've got another example, I think, later on.
Yep.
Okay, right. So we're going to look at the proton.
Oh, yes. So let's get
proton NMR spectrum for this one.
Of this molecule. Okay, so we've seen already that there were 7 chemical environments. So let's actually look at the real spectrum that Matt recorded for us. Okay, so first thing we would do is just count the signals. Okay, I'm just going to count the signals, see how many we've got. Okay, so there's one up here, that's the first one, second one, third one, fourth one, fifth one, sixth one. Okay, so actually we're seeing 6 signals here, and we'll talk about why in a moment. Okay, but basically we will need to figure out what's going on. We expect 7, we've got 6. There must be a reason for that. So we'll discuss that in a moment. But before we do that, we want to look at possibly these two.
Yep, we have another widget, I believe.
We've got another widget associated with these two. So these ones here, these ones with the lower chemical shift, a bit like we saw when we were looking at the carbon NMR, are to do with the sort of CH3s and CH2s that are away from the oxygen, and similarly maybe over here. So what we're going to focus on are the lines that are a higher chemical shift, and those which are those that are due to the hydrogens that are near the oxygens. Okay, so we've kind of got a CH2 here, which is kind of near the oxygens. We've got a CH2 here, which is definitely near the oxygens. So what we'd like you to do really is use your correlation chart. What was the question exactly?
Okay, so the question is, how would you interpret the proton resonances centered at 4 ppm?
So you've got a signal at 4 ppm and you've got 2 ppm. But
okay, and the reason we're saying it's centered at 4 ppm, because you probably can't pick it up on the resolution that you're seeing, but actually we're seeing multiplets for most of these peaks. So actually they're actually not a single peak, but kind of a set of peaks. But they all are related to, in this case, the single resonance, or so the single nucleus, and how it's split with the coupling. Okay, so we'll let you think about that. So I think we're going to go back now and actually have a look at why we're only seeing six resonance lines.
So what we're going to do is look at the integrals, and you actually, what I'll do is I'll write these out for you, okay? So it's quite, again, there's, the resolution won't allow you to see them. So I'm just going to write down the integrals, the number of protons that contribute to each of these peaks, okay? So this one actually has 2 hydrogens contributing to it, okay? Which is fine, it's a CH2, we've already kind of discussed this. This one also has approximately 2 hydrogens contributing to it, so again, that's a CH2. The one a bit further down, towards 0, next one along, also has 2 hydrogens, so we've got another CH, that will be another CH2. I'm going to skip this one out for the time being, this one in the middle, because we'll come back to that. The one after that, oh goodness, is actually is going to have 3 hydrogens. I'm going to write CH3 there for a second. It will be 3 hydrogens contributing to it, and the last one also has 3 hydrogens. This one here, the one which we haven't done, actually is around 4 hydrogens, so it's actually 4H. Now, 4H, well, you can't have 4H in a molecule unless it's methane, of course, because you're going to have carbon-carbon bonds, which means you can't have 4 hydrogens attached to the carbon. So what could that be? Well, the only way that could fit with our molecule is it's actually a CH2 and a CH2. And what we're seeing there is we're seeing part of this chain, okay? What we're seeing is 2 overlapping signals. So one of the CH2 has a very similar chemical shift to the other CH2. So this peak here is actually corresponds to 2 resonances. So this is where our mystery is solved, essentially. So rather than having 6 signals, rather than having six resonances, we actually have 7 resonances, but one of the signals involves an overlap. So we're seeing 1, 2, 3, 4, 5 for that one, 6, 7 resonances in total, which fits what we'd expect.
It does, and I think also, because this is related to the question, so the question that we had before was why in the previous example you'd said that there were 5 aromatic protons all had were chemically equivalent. Now they weren't chemically equivalent, they were actually, there were 3 of those aromatic environments, but it was the same thing that the chemical shifts for those were very similar, so hence the fact that actually the peaks all tended to overlap. So even though they were in 3 different environments, the chemical shifts were very similar. So hence the fact that they kind of overlapped. So the same kind of principle that we've seen here. So you don't always see these very clearly defined peaks for each of the environments.
Yeah. Very often that's the case, in fact.
So, and particularly the more busy the molecule gets, the more likely you are that you're going to start to have, they're more similar.
Okay.
Okay, so what are we going to say a little bit more about?
Oh, the CH3s.
Which ones might be which?
Yeah, so you've got 2 CH3s at the end. So there's a CH3 here, there's a CH3 here, so at either ends of the molecule there's a CH3. And I guess we can kind of possibly guess which one's which. So Eleanor, which one do you reckon is the one with the lower chemical shift?
I am thinking it's going to be down to this one.
Yeah.
Because this one is slightly closer to these electronegative, the oxygens here, so we would expect this one to be slightly more de-shielded than the methyl group down here.
Yep, absolutely. I agree. Perfect.
Okay. Right, so is it time now to look at the widgets? So I will add my answer to this as well. Okay, so if we now have a look at the answers we've got, so we've got the majority are going for the proton resonances centered at 4 ppm being due to the methylene next to the oxygen atom. So in this case, we are now looking at, yes, it is this one. Just checking I've got the right, correlation chart. So we were looking at the correlation chart for the methylene protons, the CH2 protons, and we have here for the CH2 attached to the oxygen of the ester, we would have around about 4. Okay, so you can see here it's between 3.5 and about 4.5. So this one is therefore likely to be due to these methylene protons. For a carbonyl, you can see, so if we look for the CH2 attached to the carbonyl, we are, I think it's this one here, isn't it? I think.
Yep.
So roughly between 2 and 3. So this is what we are, and that's around about 2 1/3 or something, is it?
Yep.
Okay, so you can see we're seeing quite a similar, it fits with the correlation charts that we're seeing there.
Yep.
Okay.
Okay.
Right, I think we were going to look at multiplicity.
We're looking at multiplicity.
We
okay,
are.
so let's look at so we've already mentioned that these are no longer single lines, we're looking at split signals. So we're going to have a little look at, continuing with pentyl propanoate, we're going to have a look at actually the 2 signals we just discussed with the correlation charts. So let me just get up an expansion of the one at 2.3, so the one, so for the CH2 that's adjacent to the carbonyl, that one there, okay, and well, what you see is essentially you've got 4 lines. Okay, so what's going on there? So this is again due to splitting. So we're looking at this CH2 here, and what we're looking at is splitting by inequivalent protons. Okay, so we're looking at the adjacent protons that are close enough that they can interact with these protons to split the signal. Okay, so we've got 2 hydrogens there, and they are adjacent to a CH3, so they're kind of adjacent to 3 protons. Okay. So those 3 protons, again using our n+1 rule, again n is 3 this time, so we've got 3 hydrogen atoms, so 3 + 1 is 4, so it will split, this signal here will be split 4 ways, so we see a quartet consisting of 4 lines, okay, and they've got this characteristic 1 to 3 to 3 to 1 intensity ratio, okay, so that's that one.
Okay, so how would we, so obviously one of the things that we're looking at in the coupling, when we get coupling like this, is we measure the coupling constant. So
okay, so we need to measure the coupling constant here. Okay, so what you do in the on the website and in the module materials, you have a sort of ruler that does it nicely for you. Quite often in the lab, you've kind of got to do it, you know, a bit more manually. Okay, so we've got what we look at really is the separation of adjacent lines, okay, in our quartet, okay, so that and that, for example. And what we do is take the chemical shift value. So I'm going to have to approximate this slightly. So this has a chemical shift of about 2.35 ppm, approximately, and this one has a chemical shift of about 2.33 ppm. So you've got a little, the difference, the separation between those 2 lines is therefore the difference between those 2 numbers. Okay, and to convert that, and these are normally quoted in hertz, okay, so to convert that separation, which sort of measures how strongly these protons are interacting, all we have to do is multiply that difference by the NMR spectrometer frequency, which we saw earlier when we were doing the video was 400 megahertz. So all we have to do is multiply it by 400, okay, and I mean, because I've done it before, I know what that comes to. So that minus that times 400 will actually equal about 8 hertz. Okay, so the splitting of these protons by those protons is about 8 hertz coupling.
okay, so in this particular example, we actually had the chemical shifts for each of these lines, but sometimes you might actually have to take out a ruler and actually measure it yourself to work out the distance between the coupling constants. So I have a question here. So why are we not seeing the coupling? So obviously when we had the carbon NMR, we saw coupling with the protons. So why are we not seeing coupling with, in this case, with the hydrogen with the adjacent carbons?
Okay, so it's about the relative abundance of the NMR active nuclei. We've got our table here.
So this is a kind of a similar version to the one that you've got. It's slightly different because we've got a couple of extra isotopes added onto the bottom that we need later on.
So you've sort of seen that you've got protons and they've got approximately 100% abundance. The one we're going to move down is to look at its carbon-13. And carbon-13, even though it's NMR active, spin half nucleus, has a very, very low abundance, natural abundance, about 1.1%. Okay, so approximately, therefore, 1 in every 100 molecules will contain carbon-13. So therefore, there's a very, very small proportion that will interact with the proton. So the interactions, therefore, it's quite a low intensity. So you just don't tend to see it in your proton NMR because it's just such a low abundance.
Okay, right. So I think we were going to have a look at the
other one.
The triplet.
Okay, so let's have a look at the other one. So this again is the signal we looked at previously. So this is the one for the CH2 that's adjacent to the oxygen. Okay. And it's a triplet, okay, and why is it a triplet? Well, we're looking at this CH2. It's adjacent to a CH2, okay, and as we discussed previously, these two hydrogens are in a different environment than those two hydrogens, so we're going to see splitting. But in this case, well, N equals 2. N equals 2 in this case because there's two hydrogens, so it's going to split N plus 1 ways, so therefore N plus 1 is 2 plus 1, which is 3. So we see a triplet.
Okay, right. So this brings us on to the next widget question. So if I just extend this up here. So we have actually measured the coupling constant between the lines, and actually we have the answer to that in terms of chemical shift is 0.017 parts per million. What we would like you to do now is to tell us which one of these options relates to how you would describe the coupling constant for this particular coupling that we're seeing here. So while you're doing that, well, I think we were going to talk a bit about the 400 megahertz and why we use the 400 megahertz. But before we do that, I wonder if it's worth emphasizing again the key point about the fact that actually what we're seeing in this case is coupling between the protons that we're studying, in this case these ones, and in the adjacent set. We don't see coupling between the two in the same chemical equivalent set. So if they're chemically equivalent, there is no coupling. You only see it, as I say, for the ones in the next, attached to the next group, effectively. Yep. Okay, so why do we have 400? Why do we call it a 400 megahertz? Well, this particular spectrophotometer, the 400 megahertz that you saw in the video, has a magnetic field strength of 9.4 Tesla. So at this field strength, protons, so our proton nuclei, will actually come to resonate around about 400 megahertz, and it's the frequency of the resonance frequency of the protons that actually give the name to the spectrophotometer. So in this case, I say it was a 400 megahertz. So if you have other spectrophotometers, they'll have a different field strength. But the key thing to note is that we use the same spectrophotometer to measure the spectra for different isotopes. So for example, we would use, so in this case what we would do is we would just tune the spectrophotometer to a different resonance frequency. So you would be studying the nuclei and looking at, so in the case of carbon-13, you'd use the same spectrophotometer, but here you would be looking around 100 megahertz. So other common nuclei, and one that we'll consider later on, is for the 19-fluorine, which would come to resonate about 376.5 megahertz. Other ones would be 31 phosphorus, which is 162. So you can see here that they're all at slightly different frequencies, which is what enables you to study the spectra and not have to worry about interference with, say, the protein peaks appearing at the same point that we would see for the carbon-13. So that's why we can kind of get the different spectra. Mm-hmm. Okay, so let's have a go and have a look now and see if you have... I shall pick an answer here. Okay, so the vast majority of you... Actually, it's not a vast majority. We're pretty... Oh, it's changing as I speak. Okay, so backwards and forwards. Okay, so we're kind of more or less split between 3J1H1H equals 6.8 hertz, or 2J1H1H equals 6.8 hertz.
Okay, so let's have a look at it. So we were looking at these protons interacting with those protons, and all we have to do to find the sort of the J value, I should say, or the number of bonds, is count the bonds. Okay, so we're looking at the number of bonds between this hydrogen atom and, say, that hydrogen atom. So maybe I'll make it a bit bigger. Just redrawing it. So this one is going to be 1, 2, 3 bonds away. So it will be a 3-bond coupling. So it should have been a 3J H coupling.
Okay,
constant.
and in terms of the coupling constant, because we're measuring it in hertz, so it is actually 6.8 hertz. It would be the correct answer.
Yep, 6.8 hertz, so 0.017
times 400.
Times by 400, yeah.
Yeah.